Hello BNG312 class, and welcome to the pre-lecture for the group exercise number 1, which we will do on Friday, about mass balances. So mass balances. So if we're designing a new process, mass balance is a very important first step. So we are trying to basically do our bookkeeping, as I said in class, while at the same time we're also applying the law of conservation of mass. And you might notice interchangeably that we use either the term mass balance or material balance. And again, these terms are interchangeable, so they mean the same thing. But essentially, we're applying the law of conservation of mass, and this is what we do as engineers. We apply theories, laws, etc., and make something practical out of them. So mass balance is the first step in that. So it's an exercise in accounting, but it's accounting for material. So you might be used to accounting for money. This is simply accounting for where is the material going. So we have inputs, we have outputs, and they all should equal up. Mass balances are used in industry to calculate the flow rates of different streams either entering or leaving a process. And of course we define the system boundaries of that process. So we can put together a general mass balance, and we can look at a process where water is the only component of both the input and the output streams. So that might be something like a cooling tower, let's say, where water is used to cool some kind of process. So water is neither being generated nor consumed in this simple example. Likely all it's doing is just changing pressure, temperature rather. Perhaps pressure a little bit. But the flow rates, Q in, designated Q in, and the flow rates out, designated Q out, would be the same. So Q in would equal Q out. A very simple mass balance. And we saw in some of the exercises we went over in class that certain components are as simple as Q in equals Q out. But suppose we have a mass balance that involves some kind of reaction or something. We examine a process where propane is the input and output stream. So we have Q in for propane and Q out for propane. So we have the rate of propane leaving the process boundary, which is Q out, is different this time than the rate of propane coming in. So let's say, and this would make the most sense, that Q in is greater than Q out, and that would probably be the most likely scenario, like we said. So what could be happening here? We have Q in, the amount of propane going in is greater than the amount of propane going out. So something's happening to the propane. So it could be that a reaction has taken place and consumed some of the propane. It could be that we are missing an output stream somewhere that contains propane. It could also be that there's a propane leak. So let's think about this. So we know there's a difference between the amount of propane going in and the amount of propane going out. We know a reaction has gone on to deplete some of the propane. But if this is indeed the case, what do we know about that? The propane didn't just disappear. So what could be happening here? It could be that there is something else in the output stream. And that would have to be the case if there is some kind of reaction going on involving propane. So propane would have had to have turned into something else. Maybe carbon dioxide. That's what you get when you burn propane. So it could be that we've got carbon dioxide going on here. So in the real world, we wouldn't really be asking this question per se. We would have an idea, we would know what process we're designing here. We would have either some small-scale lab results like we had with our xanthan gum mass balance, or would have some kind of governing equation like we did with our ethanol to acetic acid mass balance. We would have a general sense of what our input and output streams would be. So we would know we wouldn't be missing a whole stream of something. we would have a general sense of what our input and output streams contained. So we would know that, okay, there's less propane in Q out, but there is also some carbon dioxide appearing. So we can reasonably assume that propane is converted to carbon dioxide. So for that kind of process, we would have an idea of what our mass balance equations would be. We would have a mass balance equation for propane, where propane in plus propane generated equals propane consumed plus propane out. We would also have a mass balance for carbon dioxide, where carbon dioxide in plus carbon dioxide generated equals carbon dioxide consumed plus carbon dioxide out. Maybe we have a carrier gas as well, and that we can probably assume that this is going to act like nitrogen does in our xanthan gum and our acetic acid examples, where carrier gas in would equal carrier gas out, so it's a tie component. And the process question would be, well, would the catalyst or biocatalyst, whatever is causing the reaction of propane to go to CO2, would it be immobilized and remain in the process boundaries? If so, then great. We don't need to think any more about it in our mass balance. We've got all the components we need in our mass balance. If no, then we have to include the catalyst in the mass balance, because it's going in and then it's coming out along with the rest of the gases. But also it's important to note that, well, we don't have a carbon dioxide stream going in, or at least we can assume, and we're not generating propane. So there are certain things that we are not doing, and those can be set to 0. So the propane generated could be set to 0, carbon dioxide in could be set to 0, and the carbon dioxide consumed could be set to 0. So thus our mass balances would look a little bit different than they're written here. Propane would look like this. Propane in equals propane consumed in order to get carbon dioxide, and also plus propane out. And for carbon dioxide, since there's no carbon dioxide in or carbon dioxide consumed, carbon dioxide generated is going to be equal to carbon dioxide out. And those can be our mass balance equation for all the components. So we could potentially set up a mass balance table that can show us these things. So again, we know we have an input stream, we have an output stream, and something is going on in the process unit right here to convert propane to carbon dioxide. So we have a certain amount of propane going in the input stream, no carbon dioxide, and we have carrier gas potentially. In the output stream, we have a certain amount of propane going out. We now have a certain amount of carbon dioxide, and depending on the stoichiometry of the conversion, propane to carbon dioxide, that would dictate exactly how much is in the propane portion and how much is in the carbon dioxide portion of each stream. And then the amount of carrier gas would be the same, because again, if it is there, we would assume that it is a tie component. Okay, and so with those things, if we had values for anything, we could then solve our mass balance. But one final thing to note is that I always ask you to define the system boundary. So say we look at the propane system, which of the following system boundary definitions would be correct? Would it be system boundary A here, where we're circling simply the process unit, and you have streams going into or out of? Or would it be system boundary B, where we're essentially circling the whole thing, including, it would seem, the streams in and out, as well as the process unit? Well, the answer to that is that A is technically correct. The system boundary, when we talk about mass balances, should not include the streams in and out that we're trying to solve for. So when you're faced with a situation where you're asked to draw the system boundary or circle the system boundary, do not include the streams in and streams out of that particular system boundary. So what are we going to do in our group exercise, our flipped classroom exercise? So you will look at a mock distillation apparatus, or two distillation apparatuses that have streams flowing into and out of. and you've got a little mixing point right here where an extra inflow is coming in. And you're looking to separate component A and component B. And these flows are a certain amount A and a certain amount B, and that's it. So you're essentially doing your bookkeeping for these components A and B. And they vary depending on which flow they're in. And we're going to solve for at least 3 different flows. And we can define several different system boundaries. So we can define a boundary, say, around distillation 1, distillation 2, etc. Okay, so what you want to do before we go to class here and do our group exercise, you want to watch the video slideshow here, and then when class time comes, get into groups, and I will have separated you into groups, and you will see a grouping sheet posted along with this video and other things you'll need for the group exercise on Friday. You want to answer the questions in the handout, work with your teammates, write out the mass balance, and again solve, fill in the tables and all that. Do this in groups and then hand in the assignment at the very end of class or whenever you finish it. It should be noted that this is not a traditional homework assignment. We will do this in class, so please do not come to class having already done the assignment. Work on it in class with your classmates for full credit on this assignment. And with that, I will see you on Friday in class. And if you have questions, please feel free to contact me.